In this video, we're computing the arc length of y equals e to the sine x on the interval 0 to 2 pi. And we're asked to carefully show the setup of the arc length integral, and then we're asked to use a computer algebra system, or CAS, to approximate the arc length. In other words, this results in an integral that cannot be done symbolically, so we have to rely on a numerical integration. And so the idea with arc length integrals is that we break the arc length into tiny little sections, and we call those a ds. And I derived this in another video, and I'll post a link to it real quick. But it turns out that ds is given by the square root of 1 plus the square of the derivative of the function multiplied by dx. So we've got to figure out the derivative of the function. And to differentiate e to the sine x, I have to use the chain rule. So I differentiate with respect to sine x, and that gives me e to the sine x. And then I multiply by the derivative of sine x, and I get a cosine x out of that. And I'll go ahead and just write down the square of this thing separately. And that's cosine squared x. And then when I square e to the sine x, I get e to the 2 sine x. So my total arc length is going to be the sum of all the arc length contributions as x goes from 0 to 2 pi. So when we go to our computer algebra system, I'm going to use the integrate command to start with. This is a symbolic integration tool. And what I'm doing here is just illustrating that this integral has no symbolic solution. So if I try integrate, it's not going to work. So I put in my expression for the integrand, the square root of 1 plus the square of the cosine function, multiplied by %e, that's the symbol for e in maxima, raised to the 2 sine x. And I want to integrate that as x goes from 0 to 2 times %pi, that's the symbol for pi in maxima. I hit shift enter, and maxima just repeats the integral back to me, which means it doesn't know what to do with it. There is no analytical solution. So that's why we're using a numerical approximation in this problem. And to get a numerical approximation, I switched to using the quad QAG command. That requires another argument at the end where I specify which algorithm to use, just a number between 1 and 6. It doesn't matter to us which one we use. They're all the same to the thousandths place, certainly. I hit shift enter, and I get an answer that rounds to the thousandths place as 8.238. And just double checking, we were asked to get this to the thousandths place, so that's our final answer. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.